and other projects like just a second, like sorry, I didn't prepare for the self-introduction part, but
you need to prepare.
Yeah. Sorry.
Okay. Are you finished?
Yes.
Okay, Madison. Yeah. Why not briefly introduce yourself?
Sure. So I'm Maddie, a third-year PhD student now. I just recently started working with Shandian and Mike Kirby on this physics-informed machine learning over this summer. And so I'll be talking about sort of my general research direction in this presentation today.
Okay.
Yeah.
Zhimeng.
Hi, I'm Zhimeng. Call me Zhimeng, or Pan, simply. I'm fifth year PhD student with Shandian now. My research mainly focused on Bayesian analysis on the Bayesian method for time series analysis and tensor decomposition. Currently, I am I'm planning to graduate and work on my thesis, my dissertation, and I'm also actually looking for a job. It's not a very easy to get a job at this time.
Yeah, don't get frustrated. There's a little bit that might be a little bit things you need to work on, but I'm still very confident about your job hunting. Okay, Shibo.
Hi, my name is Shibo Li. I'm a third PhD student. My research interest broadly lies in active learning, Bayesian optimization, and uncertainty quantification of deep models. So I have met everyone in this group, so except Dylan, and so that's all about me.
Okay, thanks. Xin. You are muted. You're still muted.
Oh, okay. So can you hear me?
Yeah.
Yeah. Hi. So this is Xin. I'm a sixth-year PhD student. So previously, I worked with Professor Srikumar Ramalika. So after he left Utah and went to Google Research, so I started to work with Professor Zhe since last year. And currently, I'm working on the network compression project. Yeah, that's it.
Okay, very concise. Who's next? Dylan?
Hi, I'm Dylan. Can you all hear me?
Yeah.
Good. Okay. I'm I don't know, maybe third, fourth year PhD student. I previously worked with Suresh Venkata Subrahmanian, and he left the U. And while I was working with him, I was working on causal inference. And but now I just barely started with Professor C's lab, and I'm working on graph neural networks. So that's my focus. And
Okay.
yeah.
Yeah, that's great. Nancy, you're muted.
Hi, everyone. My name is Nancy Liu. I'm a first-year PhD student, and I started work with Professor Mike Kirby and Shandian last semester. And I'm mainly working on the deep symbolic regression stuff. Yeah.
Okay. Yeah. Da.
Hello, my name is Da, and I'm also the first year PhD. I joined the Shandian's group last semester, and now I currently have two research projects. The first one is sparse Bayesian neural networks, And the second one is the physics-informed Gaussian process. Yeah.
Okay, it's great. And hopefully, I mean, you guys should talk offline. But yeah, because our group is growing bigger and bigger, it's very important that I mean, all the group members could communicate with each other and seek for collaborations, even for, I mean, hangout for fun. That's totally up to you. I think that would be very good for the whole group. And I'm also planning to invite Michael Van Walden and Tushar to join this seminar. They actually mainly supervised by Mike, but I feel like this kind of seminar is huge, useful. Actually, quite a few of my submissions, the ideas came out from you guys are presenting the papers, and also those critical thinking. I think will is very valuable. It's much more valuable than those countless boring meetings I have to attend. So yeah, so this is a really good place. So feel free to challenge and ask questions during the presentation, because we're trying to learn together. This will be very, very efficient, because if you carefully read through one paper, I mean, from my own experience, it will at least take 4 to 6 hours. Right? And but now, if you listen to others' presentations, and you will know almost everything like in 2 hours. That will save a lot of time. And also, those kind of works from different directions will kind of motivate or give you some kind of new ideas, and launch, I mean, discussions of new ideas, new projects like what Shibo has introduced, or what Shikai, he's now here, he's in China right now, but SD representations. They all gave at least I was inspired by those presentations to think about new projects. So I hope everyone will, I mean, not only listen to these presentations, also think about how those words can relate to your own research. And is it possible to motivate a new project? Yeah, and try to do that, especially for those senior guys. Okay, Madison, I think we can start.
Okay. So today I'm presenting on the neural tangent kernel and then some of my preliminary results. But the neural, well, okay, so the outline of this presentation is going to be, I'll first give an overview and the motivation of the NTK. And then it's highly dependent on the how neural networks behave in the infinite width limit. And then I'll go through the definition, and then talk about what the NTK for pins looks like, and then talk about some of my results.
Amazing. Can you first explain what's the motivation of NTK? What is NTK defined for?
So the main use of NTK is to try to explain the training dynamics of neural nets. So it's more about understanding how these neural nets evolve during the training of gradient descent. So it was proposed in 2018 initially for just standard neural nets. And so some sort of questions that the NTK can answer is how fast is the convergence to certain components of the function, and then it can tell you which components converge the quickest. And if that's slightly confusing, I'm going to specify that in the next few slides. So, and the use and benefit behind this is that there's not a lot of understanding behind when neural nets and physics-informed neural nets fail to provide accurate solutions, because sometimes they find accurate solutions, sometimes they perform really poorly, and not a lot is understood about why this discrepancy occurs. And then if you're able to understand why certain nets fail to train, you can better come up with strategies for fixing those issues. And the current method of coming up with these strategies, as you've probably read in a lot of papers, it seems like a lot of researchers come up with, they find a problem, and then they come up with a method that fixes the problem, but that method is often not really justified by any sort of theory. And so the goal with NTK is to give some type of theoretical justification for some of these mitigation strategies. And so in this work, I'm mainly going to be talking about this paper here, when and why pins fail to train a neural tangent kernel perspective. The preprint was posted in 2020, and then this year it was finally accepted to the Journal of Computational Physics. So if I say in this work or in this paper, in this presentation, I'm referring to this specific paper, if that is unclear. Okay. So the neural tangent kernel for traditional neural nets, which I'll talk about first and then get to physics-informed neural nets. But a lot of this theory, or at least most of this theory, is dependent on the assumption of infinite width. So we're assuming that the width of the hidden layers in the neural nets approach infinity. So in this presentation, I'm going to be considering a neural net with one hidden layer. And so most of the notation will be for one hidden layer specifically. And also I'm omitting the bias terms just for clarity. But the neural network theory applies to multiple depth, like sequential depths. The pins theory doesn't currently apply to multiple hidden layers, but I'll talk about that in a minute. And so,
Madison, do you have any restriction on the form of the activation function?
it has to be differentiable and smooth.
Okay, like sigmoid or tanh will be good.
Yeah.
Okay.
And so what Jacot in their work answered in 2018 is how the output of your neural network evolves during your training. And they found that under all of these assumptions, the infinite width, and then there are a couple more, that the output and actually the output at each hidden layer converges to a Gaussian process. And this is true at initialization as well.
What do you mean by this is true at initialization?
So when you first initialize the neural tangent kernel, it's already a centered Gaussian process. You don't need any sort of training for it to converge to the process.
I think this is a classical theory. You know that if for a single layer neural network, if you have an infinite wise, and if you normalize the output by 1 square root of the width, which is n here, square root of n here, you assign standard normal prior over each element in the weight, it is just a Gaussian process.
Mm-hmm. Yeah. So this is a well-known fact, I suppose. And then the Jacot and authors use this use this behavior in the infinite width limit to further define this neural tangent kernel. And so here, this is the definition of the neural tangent kernel. And so this kernel is the inner product of the derivative of the loss functions with respect to all of the network parameters. And so Ducat and others showed that this kernel actually converges to a deterministic kernel upon random initialization and as the width goes to infinity. And
so theta t here means the model parameters after t updates or t epochs.
T training epochs is what T refers to.
Okay, f is a loss function.
Yes.
And what about x? X is the input?
Yeah. And then theta are all network parameters.
Yeah, here, if from probabilistic view, theta is actually the neural network weights, right? This is essentially, if you view theta as random variable, then this kernel essentially is a random variable.
Mm-hmm.
Is that right? Or they didn't give some probabilistic view of this. They just assume theta are just some unknown parameters.
I believe they just assume they're unknown.
Okay, they didn't try to associate with Gaussian process right now.
So yes, they actually do. Sorry. They do show a relationship with Gaussian processes.
So they define this kernel as the dot product of the gradient with respect to these two input instance, right?
Mm-hmm.
With respect to the whole neural network.
Yes. So this is the sum for every layer of weights. You take the
square norm of the gradient. The square norm of the loss gradient, right?
Diagonal is the square loss of the. Yeah, I'm saying that the diagonal of this kernel is the square norm of the gradient of each training examples.
Oh yeah. If x and x prime is the same, yeah.
Yeah, but why this kernel is a random variable? So we are not doing a mini batch here.
Because Madison introduced the Gaussian process formulation for the neural network. If we assume theta are random variables.
Oh, theta is random.
Should be random variable.
Mm-hmm.
Okay.
So they show in that prior work that neural networks in the infinite width limit using this kernel converge to or are equivalent to Gaussian processes. But the proofs of that are pretty involved, but they basically derive the covariance and the mean from this kernel definition.
Also, you mean the in the limit when you have like infinite width, because the probabilistic version of neural network can be viewed as a Gaussian process. So this is the kernel of that Gaussian process.
Yes.
But if it's kernel, it should you should take expectation, right? Because if you view theta as a random variable, the kernel itself becomes random variable. If you do if you consider a covariance function or kernel function, it should be deterministic.
Mhm. So they show, I believe they use this kernel to derive the
Kernel for the GP.
Oh, no, sorry for the confusion. They do use this kernel as the Gaussian process kernel. And they show that it's deterministic. And that, oh, sorry. And that it remains constant during training. I don't think, does that answer your question? I don't.
Shandian, would you mind repeating what you were saying? I'm trying to follow that. Are you saying the kernel should be deterministic, or you're saying that because it sounds like
I said the kernel should be deterministic.
Not that it could, because I think for property 1 here, it's saying the kernel converges to a deterministic kernel.
Converges meaning as the width goes to infinity.
As the width goes to infinity. Okay.
Yes.
Oh, I saw the bottom line. So it tells about the kernel evaluated at theta 0. That means at the initialization.
Mm-hmm. Yeah.
Yeah, but still confused. Like I mean, if it's okay that you build up a connection between the neural network and Gaussian process, but if you want to make this connection, you have to assume the weight of the neural network, namely theta here, are random. They're random variables. So that means if you assume theta is random variables, then this neural tangent kernel itself is random because it is function of theta as well.
Mm-hmm.
But if you look at the Gaussian process, you're supposed to integrate all the theta, and you come out a kernel function between the inputs x and x prime. That should be deterministic. So you say that the kernel converges to the deterministic kernel. That means if you make the d1 goes to infinity, this kernel becomes deterministic.
Yes.
Okay. So it converges almost surely, isn't that? Because if you're saying a random variable, a random value converges to some deterministic function, you must associate with some probability statement, like almost surely, always probability 1. Do they provide a statement?
Not that I can recall, but I would need to look into the original NTK paper to see if they.
Yeah, I feel like it's more natural to take an expectation of this dot product, and then you'll take a d1 to infinity, and then converges to some kernel. I feel more natural like that. It's kind of like a little bit weird. You put a random function. Essentially, it's random function determined by theta, and when you incorporate infinite number of theta, that function becomes deterministic. That sounds a little bit weird to me.
Actually, in the original paper, the convergence here should be probabilistic convergence. The kernel convergence converges in probability to a deterministic
okay.
kernel.
Yeah, that makes sense. That makes sense.
It's not a point-wise convergence. It's a probabilistic.
Convergence in probability or in distribution?
In probability.
Probability.
It should be in probability.
Okay.
Okay. Yeah, that makes sense.
Okay.
Yeah, let's continue.
Okay, so now I'm going to just introduce a simple PDE modeling problem that they discuss in the paper. And it's just the 1D Poisson problem with a simple fabricated solution, which looks like this graph here. And so the PDE is given as this set of equations. Is everyone familiar with PDEs or?
I think so. You might.
I'm not. So if you want to give a background, if that's okay with you.
Okay.
Sure. So U here is some unknown function that represents the solution over here. So we don't actually know what that function looks like, but we do know what f is, which is called the forcing function. And in this example, f is equal to this equation. And we also know that f is equal to the second derivative of whatever u is. And so the question is, can we use this relationship to better infer what u is? So we're trying to use this, these physical properties to encode additional information into neural nets to constrain the solution space. And so this equation, it models real world phenomenons. I forget exactly what, like, does anyone know of any examples?
Doesn't matter, Mass. I don't know as well. Just introduce like what is partial omega means. It should be the boundary condition, right?
Oh yeah. Okay. So this represents the set of points on the boundary. So in this example, it would be this set of points. So we know what the solution at this set of points is, and it's just 0. These are called the boundary conditions. And this set of points here refers to all of the points within the domain, called the residual points. Okay, does that help a little bit?
Yeah, awesome, thank you.
Okay. And so when we solve these equations, we're given this residual data, and we're trying to find this unknown solution. So this is the actual data that we are given, usually in standard pins. And so the way pins are formulated is by a composite loss function that looks like this, where where the first term evaluates the loss on the boundary points. So this is comparing what this neural net here, the loss between the true solution and what it outputs specifically for the boundary points. And then we also measure the loss of these residual points. And so that's the difference between the error in the residuals, essentially. So in pins, you assume that you can approximate u, which is your unknown solution, with this neural net. And so from the previous slides, we know how this term here behaves, but we're unsure how the PDE term behaves in the infinite width limit, or the training dynamics, basically. We don't know what the training dynamics are, which is what Wang and Paris Perdicaris, they answer this question in this paper.
So Madison, reverse assumption here, I mean, if they want to apply the NTK, they actually should assume the pin only has one layer, and also the y sub layer goes to infinity.
So they, yes, they do. Those are both assumptions, but they posit in their paper that their NTK for pins theory should apply for multiple hidden layers, but they don't. Their proofs and things don't actually apply.
Okay. We just want to make sure what is the reverse hypothesis underlying their analysis.
Mm-hmm. And another assumption is infinitely small learning rate. And I'll talk about that, why that's necessary as well. So this term you can derive from the bottom term pretty easily. And so we want to know, or the question is, how does this term evolve? So in this paper, they wanted to answer a few questions. Mainly, do those same properties that the NTK for standard neural nets also apply to the NTK for pins? Meaning, does it converge to a deterministic kernel, and does it remain constant during training? And so in this paper, they answer that that is true. And so before we talk about how they, or like what the answers are to these questions, or how they find that the answers, I'll first go over the form of the NTK for physics-informed or neural nets.
One question, Madison. So you said that the property of this NTK kernel is that it's remain constant during training. What does that mean?
The kernel doesn't change or update much as training occurs.
So I mean, even the theta is updating continuously, the kernel itself doesn't change?
So the intuition, I believe, is that in the infinite width limit, any small change in these parameters, in the neural net parameters, would result in a large change in the output. And so the idea is that the parameters of the neural net don't change much during training in the infinite width limit. Therefore, the kernel also doesn't change.
Oh, so you mean, it remains constant means at the limit it remains constant during the training.
Yes.
It's not like for a finite neural network, like I only have 10 neurons, and you directly calculate NTK. That will change, right?
Yeah, slightly. I have some figures on that as well. But yes, practically that doesn't apply yet. Anyways, it would be interesting to come up with a formulation for that. But so this equation here is the form of the training dynamics of the pins loss terms, where this is the NTK of pins. And so to derive this formula, we first need to consider gradient flow. Which is just, I don't know if I need to explain gradient flow or not, but
one second, are you trying to show how you get this the bottom part? How do you how is it derived?
Yes, yeah.
Okay.
So to start with, gradient flow is essentially, if you think about gradient updates, the gradient descent updates, they look something like this, where you have a learning rate, and then you take the derivative of the loss. So then if you kind of rearrange this formula, you get that, let's see. You get a form that looks like this. And so if this learning rate here is infinitely small, you get the gradient flow shown here. So that's why the infinitely small learning rate is an important assumption as well. Okay. And so if we consider the pin loss function again, and this is, specifically for that modeling example that I introduced, but in the paper they say that it should also apply to other differential operators. And so what we want to know to understand better pins and the training dynamics is how these two terms evolve along the trajectory of gradient descent. And so that would be described by the derivative of each as they change during training. So this is like what we're mainly interested in. And
so what does DLU means? L is the operator.
L is, yes, it's the differential operator. So you can replace that with UXX. So from here, you get, if you take the derivative of let me see. Okay, so if you apply the chain rule here, sorry, you get du d theta times d theta dt. And we just derived what d theta dt is from the gradient flow. So we can replace that with du d theta times the derivative of the loss, which is from this equation here. And so when we replace that and we simplify this equation here, I'm not going to go through the full sort of simplification, but you end up with you get U minus G. So this term here times the inner product of U d theta d U d theta minus UXX minus F So this term here times, again, the inner product of these derivatives. And then from here, you can do some manipulations. And then if you do the same sort of derivation for this term here, that's how you end up with this form.
Okay.
That,
so the
is that clear?
KUUT is actually, oh, what's the definition of KUUT? It's a
of what? Sorry.
I mean the neurotendral kernel part at the bottom. So what's the definition of KUUT?
Mm-hmm. So.
Oh, okay. Yeah, I can see it. So KUUT is actually the function at among the boundary points.
Mm-hmm.
Okay.
Yep.
But here is a dot product of the gradient of the U rather than the loss.
Yes.
And similar definition applies to KUR, KRU, and KRR, right?
Mm-hmm. Yeah.
Shall we call this as NTK as well?
So they call it the NTK of pins.
NTK of pins.
Yeah.
Okay. But it's just actually it's actually the gradient of the neural network's output rather than the loss of the neural network.
Right. Yeah, because that's what you're ultimately interested in, is what the output, how the output behaves given training.
Okay.
So this form here describes the dynamics that I've been mentioning this whole presentation for pins specifically. Okay. And so now going back to one of the important questions that they in this paper wanted to address was if the NTK of pins also converges to a Gaussian process. And so this was shown previously, and in this work, they do show that it converges to a centered Gaussian process. The derivation of this is pretty complicated, so I wasn't planning to go through that. But the important point with this finding is that there's a pins GP correspondence for linear PDEs. From what I understand, this isn't practically too useful at the moment. My guess is due to all of these assumptions that they require.
Well, one thing, one question, Madison. So can you go to the previous slide?
This one?
No, I mean, yeah, this, no, the next slide. So this is just tells us, this is by Jacob. The blue bounding box shows that your NTK kernel. Actually, I don't quite catch the conclusion of GCOC here. So it means that in distribution converges too. doesn't mean that you have like infinite number of training points, or still assume your neural net wise goes to infinity.
You're still assuming the width is infinite.
The width goes to infinity.
Mhm.
And then the covariance function here should be determined by the NTK, right?
Mhm.
And okay, because it's well known that if a Gaussian process, if some function is sampled from a Gaussian process, then the second order derivative will be another realization of Gaussian process where the covariance is the second order derivative of the original covariance function.
Mhm.
And what's the new thing here? So they mean that from the neural network perspective that if at the limit your neural network output converges to a Gaussian process, then the second order derivative of the neural network output will also converge to a Gaussian process with where the covariance is also second order derivative of NTK kernel
Mhm.
at the limit.
The second order derivative of the original covariance, which is determined by the NTK.
Yeah, that will be the limit of NTK kernel. The sigma one here. The sigma one here, in this case, because sigma one can be viewed as a limit of the NTK kernel. Like when their wave goes to infinity.
Hmm.
And the second conclusion says that, okay, for the same neural network, if you take a second order derivative with respect to the input, when you make the wave to be infinitely large, and it also converges to the Gaussian process, but now the covariance is also the second order derivative of the NTK kernel at the limit.
Mhm.
Then I think previous when we introduced NTK kernel, I think that F shouldn't correspond to loss. It just corresponds to the output of neural network, right?
The what?
I mean, in early slides, you introduced the definition of the NTK kernel.
Mhm.
I think it's a dot product between some partial F over partial theta and partial F over partial theta, right? That's the early slides. I think that F should indicate the neural network output rather than some loss function, because you can change loss function. I think you still need to go to the previous slides. Yeah, F here. F here should in general be viewed as the neural network output, isn't it?
Yeah.
Okay, that makes sense. Otherwise, in their NTK kernel, they call it NTK, but they calculate the kernel in terms of the neural network's output with respect to the parameters.
Yeah, so this is the output, and this, so this is the neural network output, and then this form here comes from the manipulation using the loss.
Okay.
Which is similar.
So you mean Sifan and his advisor Paris, they based on this gradient flow formulation show that show the second conclusion, right?
What do you mean by second conclusion?
You mean the slides we just discussed? There's a blue box There's a
Oh,
blue.
yeah, sorry.
Okay. So their key technique is based upon the observation of this gradient flow.
Yeah. And so, yeah, their contribution is mainly with respect to the differential operator portion of the PDE.
Oh, that's interesting. That actually tells us if you use this specific loss function, because this gradient flow is also determined by loss function.
Mhm.
So that means this loss function is meaningful. It can give you the guarantee that the second order derivative you also converges to a Gaussian process.
Mhm.
Okay.
Yeah. And from what I've seen in pins, at least, it's the only loss function that's really been studied at all for pins. If someone knows of another reference for that, let me know. But yeah, it does matter for their conclusions. Okay, and then for the second point that they wanted to figure out is if the NTK of pins converges to a deterministic kernel in the infinite width limit. And they show that, yes, it does, essentially is the gist of this. The proof of this is also pretty involved. So I wasn't going to go through that either, but they do show that.
Okay, the speciality of this this NTK kernel for pin is that it includes the kernel between the boundary points and the residue points.
Yeah.
Okay, this is different from the ordinary neural network loss because you don't need to differentiate boundary points and residue points.
Mhm.
Okay.
Yeah. Okay, so that's essentially the same. They showed some numerical results, kind of somewhat demonstrating these 2 points a little bit. So they test on that model problem that I introduced, the 1D Poisson, on several different network widths. And this plot on the right here shows the relative difference of the kernel, the NTK, relative to the initialization. And so it shows that when your width is small, the kernel changes quite a bit. But then when your width is very large, the change is much smaller. And this aligns with the theory as well. And also, as your width gets smaller, as the width gets smaller, it mostly remains the same. And okay, sorry. As the width gets larger as well, they're, I guess you can't quite say this, but they're about the same kernel.
Yeah, the relative difference is very small
Mhm.
for larger width. But I'm curious to know to see why in figure A, the left figure, we have a large width. The relative change of the model parameters is also tiny.
You're saying for small width?
For large width, like width 500, the blue line. So you can see the left figure shows how your model parameters vary along with the training iterations, right?
Yeah. So this is aligned with that intuition I discussed earlier, that if your model parameters don't change much, which they believe that's true because, and there's a proof for this, I think, but the idea is that as the width gets larger and larger, these changes in the parameters will result in a large change in the output, which means the parameters aren't going to change much during training as your width gets larger and larger, is why the width is so small here, or the change is so small.
So this training is conducted by Adam.
I believe so, or I'm not sure.
Yeah, maybe it's just because the Adam or other SGD, they're trying to do adaptive step size.
Mhm.
And
yeah, I'm not sure if they use Atom. I think that
how they compute the theta zeros, the second norm of the theta zero, just summing over the square of the parameters?
I think so. It's just theta zero is the initialization, right?
Yeah.
So,
Then you have wider neural nets. Then you have more parameters. So right. So if you have 500 parameters, basically the number of parameters grows quadratically.
it is norm. You take square summation and then take square root.
Oh, okay.
It just tells us that the relative change of the whole bunch of whole set of model parameters is kind of tiny.
Okay.
Yeah, I'm just curious to know how is it because SGD takes a particular small step size, or it is indeed so? Because if you run LBFTS or if you run gradient descent with some Frank Wolf updates guarantee every time you're gonna decrease the objective function. If in all the cases such change is tiny, then I think that's that's reasonable. Otherwise, I don't know. Yeah.
You're saying for each type of algorithm?
Yeah, like if you have a lot of like optimization algorithms. If you SGD, you are free to choose step size. And usually our experience is that if you take a large step size, the objective function will perturbate wildly.
Mhm.
So you have to make the step size to be very small, but it's too small. Maybe you just run 10,000 iterations. It doesn't move forward much.
Yeah, I think that's one of the major disconnects between their theoretical results and the practical application. Because
I'm really curious to know if they run LBFTS. And
they're doing full batch gradient descent.
Yeah, if you use gradient descent, if you use normal gradient descent, to ensure every time you're going to decrease the loss function, you have to smartly control the step size. One commonly used technique is called Frank Wolf. Or you can use second order method like LBFTS. It converges faster and it can smartly choose the step size as well. I mean, if those results come from running LBFTS or gradient descent with Frank Wolf update, then I think it's a really good justification of their theory. Otherwise, did you see any setting in their experiment?
Not that I remember right now, but I can go back and look for that.
I just checked their code. They use both Adam and standard gradient descent. I don't know how they generated this figure.
Okay. Anyway, let's continue, Max.
Okay. So if you combine those two results, that being, does the NTK converge to a deterministic kernel and remain constant during training? You can say something like this. And this is useful because okay, so this is useful because if you consider the training dynamics equation that we discussed earlier, that you can, so this means that the training dynamics of your pin can be described using this deterministic kernel that remains static during the training, under all of these assumptions, of course. And this is useful because it gives you the dynamics at the very start of training as well, so you can kind of see how your training is going to behave from the very beginning.
So they are making assumption that, okay, they got a very wide neural network, so that we can assume this this NTK is approximately constant during the training.
Yes, so it's still under the infinite width limit. And then, so in practice, it's not, the theory doesn't exactly apply, but they show with those numerical results that it seems to be true.
So they want to look at the, okay, if you assume the NTK is constant, like K star here, they want to use this this actually is ODE, right? They want to use this ODE to look at the training dynamics or diagnose the problem.
Yes, and so they're using this because see, this form you can derive a certain eigenvalues decomposition form, which I'll
is the K star. Look at eigenvalues and eigenvectors of K star.
Yes, and that gives you like the convergence rate for certain components of the function. And so it also tells you, I'll talk about that more in a second, but this also tells you that you can approximate the network's outputs for arbitrary test data during gradient descent if you specifically consider if t approaches infinity. And so this is equivalent to kernel regression here, their derivation. But they say, they make a comment that this isn't practically useful because what do they say? That the NTKs are not in practice positive semi-definite. I think
it's not positive semi-definite.
Yeah, not often. So they say, yeah, they say this isn't super useful.
Why is not positive semi-definite? It's a dot product. Dot product should be.
It might not be invertible.
Yeah, but that should be positive semi-definite. Oh, it's okay.
Sorry, yeah, it is positive semi-definite. Yeah, you're. It's the problem is that it's not invertible. I mixed that up. Sorry.
Assuming they use this ODE, I mean in the first line, in the slides, they can derive the test at a limit. Will have this form, right?
Mhm.
Okay.
Okay. So they show that, but then they show kind of the main use of this NTK is that it diagnoses, or it shows that NTKs or pins are spectrally biased, which means that neural nets are unable to learn high frequency functions. So they use the NTK in this paper to diagnose that issue and then come up with a fix for that particular issue. And the way they do that is they use this form here of the training dynamics and the assumption and the fact that they derived. And then they come up with this form here. And this should be just U, X, X. But what this means is that, okay, and well, here are a few of the steps to get to that point, if you're interested.
What is Q? Q is a matrix or Q is a function? Q is matrix.
Q is the SVD. They take the SVD of K, and so Q is the matrix from this SVD.
SVD gives 3 matrices.
Yeah, so they get this here, and then they rearrange this formula, move the Q to the left, and then to get this following this last equation.
Okay, so they decompose K. They decompose K as in the form of SVD.
Yeah.
SVD. So the Q should be the. That's weird. Okay, it's not symmetric. For the SVD, is it? It has a left singular matrix and right singular matrix. They assume they are the same, right? And the diagonal part, why they put a exponential term here?
Oh, the exponential comes from. They're saying it's the solution to the ODE here. So they're saying, like, if we look at du dt first, they're saying a solution.
Oh, okay. So this is actually the solution of this linear ODE.
Yeah.
Yeah, it's a linear constant time, linear constant ODE. Okay. And then they subtract both sides by this GXR. Okay, GXB and F of XR. They get this. They get away of this identity, and then they leave. They left this e to the power of K0t. It's a matrix exponential, but what is Q? Q is the
eigenvectors.
Q is eigenvectors. Yeah, I assume this is kind of a eigen decomposition over the matrix exponential, right? Because matrix exponential is different from I mean ordinary exponential. It's not to take n-wise exponential.
Mm-hmm.
Yeah, I'm wondering if this is just or the so I mean Q is eigenvectors of K0.
Mhm.
Okay, then there must be some conclusion about this exponential. That means e to the power of minus exponential is the can be decomposed in that form, like Q e to the power of eigenvalues times T times Q transpose.
I believe so, if I understand what you're saying correctly. But
Can I take the previous slide? We'll look at it again. Yeah, this might be some property. I don't know, because matrix exponential is not easy to compute. It's okay. So they multiply the Q on both sides on the left, so they get this. Okay, yeah. They must apply some mathematical conclusion about matrix exponential.
yeah, so they say that, so this here is just another form of what I just showed, but I'll just go back here. This is saying that the ith component on this left-hand side.
So the rule is the G, XB, and F of XR is Y train. I mean, your next slides, you just write them as F, X train.
Yes, Y train. Mhm.
Okay.
Yeah, so the ith component on this left-hand side converges, or it decays at a rate of e to the eigenvalue. So this gives the convergence rate for a particular component.
Okay.
Is what they conclude from that. And so this is saying that these eigenvalues characterize the absolute, how the absolute training error decreases, and that the particular components of the target function with larger eigenvalues will converge more quickly. And there have been prior works that show that the components of the target function with the largest eigenvalues are lower frequency. That was in a prior work. And then so that's how they conclude in this work that pins are spectrally biased, because typically in their numerical experiments, at least, here, the eigenvalues, there are a few large eigenvalues and then they quickly drop off. So
Okay.
they sorted the eigenvalues of the NTKs. You can ignore these probably. They sorted the eigenvalues from largest to smallest. So there are just a few very large eigenvalues and then a lot of small eigenvalues.
So it basically says some components underlying the training are converges much faster than the remaining.
Some components of the target function.
Target function.
Yes.
But how does it relate to the high frequency and low frequency?
So there was a prior work that they cite that finds that the eigenvalues associated, or the eigenvalues that are larger are associated with lower frequency components, and then eigenvalues that are smaller are associated with the higher frequency. And so if all of your, this means that the lower frequency components of the target function converge very quickly. But then if your function has any sort of high frequency components, they'll be very slow to converge.
Okay, so the function here, you mean the ground truth, right? If you ground truth,
Mhm.
the ground truth, our target function, it contains low frequency functions. The learning procedure will converge very quickly for those to learn those to capture those low frequency components. But for high frequency components, it converges very slow.
Right. Yes. So an example could be if you have a target function that looks like this, there's the pen would very quickly train to end up looking kind of like this. It would find this shape quickly because it's the lower frequency component. And then it would take a very long time to convert to this higher frequency if it does at all.
So the prior works, how do they justify this correspondence between the low frequency component and the faster convergence in loss?
I'm not exactly sure. I would need to look through them.
Okay. But they give some theoretical justification, right? It's not just empirical.
I believe so.
Okay. Yeah, that's interesting because essentially the left-hand side is a kind of like combination of the training error. It's not just the original training error. You do some transformation of the training error, right? So I don't know. Yeah, that might correspond to, like, if you do some eigen decomposition, those are eigenvectors. You're essentially combining those eigenvectors in terms of the training error. Maybe different set of eigenvectors corresponds to the low frequency component and high frequency components respectively. Okay.
Yeah, and in a subsequent work by these authors, they look at these eigenvectors and the frequencies of the eigenvectors, and they plot some of them, and they do show that the eigenvectors corresponding to larger eigenvalues, when they take this eigen decomposition, or the SVD, sorry, that they are lower frequency. So they show some plots of that.
Okay, they give some empirical demonstration. That means based on this observation, if your NTK, eigen decomposition, eigenvalues are all quite large, that means the training will be much easier.
Yeah. So based off of the NTK, you'd ideally want eigenvalues that are, all large or all flat. And then, so their mitigation strategies that they propose are trying to flatten out these eigenvalues.
Okay.
And so that's the main practical use of the NTK.
Okay, so yeah. Let me think about. So that means if you just look at the NTK of the pins, if you view like the distribution of the eigenvalues is something like a very short high values, and then drastically truncate to very low level with long tail, that's not good, right?
Right.
We expect that you have a kind of a larger number of big eigenvalues with just a few very short low tails. That will be good.
Yes, based off of the conclusions they draw here. Yeah.
Okay.
So in this paper, they use this observation given the NTK and their theoretical justification to come up with a reweighting algorithm that basically just reweights the two different loss terms in the loss function during training. And these weights are based off of the NTK eigenvalues. But they show that this method doesn't always work all that well. And then in a following,
You mean the reweighting?
yeah,
loss terms?
the reweighting, it sometimes works, but it doesn't target the actual issue of these eigenvalues, the eigenvalue discrepancy.
Yeah,
okay.
if it's eigenvalue, if it put reweight, do they update the weights as well, or they just assign different weight for the boundary loss and the residue term?
Do you mean based off of the NTK, or
based on their remedy? They said they got some remedy to reweight the loss terms, right? So I'm just curious that they fix those weights like lambda 1, lambda 2 at the beginning and during the training, or they kind of like it also iteratively update lambda 1 and lambda 2.
Yes, at the beginning they're initialized to 1, but then yes, during training they're updated every few.
If they update the lambda 1, lambda 2, their calculation of the NTK will change as well, right? Although it's not changed, but the ODE, the gradient flow will change. Because if you derive the gradient flow, you got actual weights lambda 1 and lambda 2. Oh, yeah, I mean, it might not change too much. So I mean, after that, when they do the eigen decomposition of the NTK kernel, it becomes more the eigen values distribution becomes more flat.
Not in this work is why it's not foolproof. So they yeah, they say that it doesn't actually address that specific issue, but in a following paper they do come up with a method that does flatten out the eigenvalues.
Okay. Yeah, I'm just curious, if they update lambda 1, lambda 2 jointly, then lambda 1, lambda 2 should be a function of time t as well, right?
Yes.
Then they do the analysis. I mean, if they do the same framework analysis in the same framework, they need to solve the ODE. Then the ODE is not time invariant. It's time dependent because it's also dependent on lambda 1 and lambda 2. Did you take a look at their analysis or just look at their conclusion?
I looked at the analysis, but I don't recall. In all of I'm not sure. I would need to relook.
Yeah, because in the discussion you just mentioned, like if you fix lambda 1, lambda 2, like 1 and 1, then the gradient flow, which is essentially a linear time invariant ODE, they have an analytical solution so that based on that solution, you can do the eigen decomposition. You give it the result. Right? You can say different components of the training error has different convergence rate. But when you introduce lambda 1, lambda 2 as time dependent, your gradient flow will be a time variant linear ODE. Then I'm not sure if it still has a nicely to deal with it still has a solution form that is nice to deal with.
Right. And so maybe that's why this method doesn't really work as all that well.
Yeah, because lambda 1, lambda 2 is I don't know how they come out methods to update lambda 1, lambda 2, but if you view the whole loss function as if you view the residue term as some hard constraints, and you construct Lagrange multipliers on that, it is essential to solve a min-max problem.
Mhm.
We talk about that when we introduced SVM in our machine learning class, right?
Mhm.
So you got a way to systematically update those Lagrange multipliers, which are
Mhm.
lambda 1, lambda 2 here.
Mhm.
Yeah, I don't know if they have used this way to update lambda 1, lambda 2. But anyway, if you update lambda 1, lambda 2 accordingly, it will change dynamic behavior, training dynamics.
Right.
Okay.
So each eigenvalue is associated with one training example, right?
They're not. You can't.
No. Okay.
Well, you cannot see that. Although, like, it is suppose you have n training points,
Yeah.
which includes both boundary and the residue collocation points.
Yeah.
It's an n by n matrix, but
Uh-huh.
you cannot see the eigenvalue corresponds to a particular training point.
Okay. Yeah. Okay. Yeah, that makes sense. I was thinking that if each eigenvalue is associated with one training example, why they take the weights, take the average of the weights and reweight the loss term, not the training example. Yeah, never mind. Yeah.
Okay. I was going to talk about the strong pin stuff now, if we want to move on from this, or if you have more questions.
Any other questions? Feel free to ask. Okay, Madison. Well, yeah, we can continue.
Okay. So when I introduced pins in the previous slides, there typically is the loss is composed of two loss terms, one for the residual and one for the boundary. But for particular types of boundary constraints, you can actually modify your neural network architecture to satisfy them exactly. And so one method to do that is to basically, if this is your neural net, you come up with some function L that satisfies these boundaries. So for Dirichlet boundaries that are 0 at the boundary, so the solution is 0 at the boundary, this function needs to satisfy two requirements. And that's just that it has to be 0 when a point is on the boundary, and then must be greater than 0 if it's if the point is in the domain. And so those are sufficient conditions for this type of function. And so some examples are these two equations here. So in my, I've been looking at a lot of the related works on these sort of hard boundary constraint physics informed methods, and most people seem to default to this simple polynomial constraint method if it's possible. So overall, that seems to be the default, but I tested both of these methods actually, and found that doesn't seem to be true. And so this red line here, this red line shows the relative L squared error of a pin using that polynomial variant of the strong boundary enforcement. And then this pink line here actually shows the relative L squared error for that second variation. So this one here.
Oh, the exponential form works better.
Yes. Yeah, so the exponential form works better. And so, but polynomial seems to be a default for most researchers. And from what I can tell, it doesn't seem like there's a lot of work on finding the best sort of forcing function for boundary constraints, at least. Most work seemed to just be trying to find methods that actually work, but not work the best. So I'm hoping that based off of this and potentially using the NTK, that could possibly lend insight into what the best enforcement methods are for a particular problem. And so this plot is showing the sorted eigenvalues of the NTKs for several pin variations.
What's the strong E? Is also the pink.
Yeah, it's the exponential. It's the strong, the exponential enforcement, and then the polynomial is the polynomial, and then these are just regular standard type pins and neural nets.
What's the co mean?
This is the collocation. So there's additional data points used in training in addition to the boundary points.
But what's the standard? I mean, the standard pin should include both the collocation points and the boundary points, right?
So yes, standard includes the collocation points, but my naming here might not be the best, but the collocation here is referring to having additional data, training with additional data points, not just residual points.
Also, I mean the difference between co and standard is that you use more collocation points.
It's not using more points. They're using rather than the residual points, the true solution as input.
Oh. Choose a solution as the input.
So just yeah, additional data.
So that means you have the boundary loss, right? You have a collocation, you have the residue term on collocation points, and you have an additional loss term from the solution.
Yes. So the collocation is given these y's as additional data rather than all data being the residual points.
Then what about data?
Data is it's a standard neural net.
Oh, okay. Yeah, it looks like, I mean, from the NTK, it looks like a strong polynomial has a better behavior.
Mm-hmm. So based off of this plot, when you compare them this way, that's how it appears. But I was talking with Mike and he said that you can't quite compare them. Like if a larger eigenvalue is better, or larger eigenvalues means that the training is better, you can't quite compare that across these different types of pins. But you can compare the shape.
But it looks like shape is also better. The pink one, we can view like most of the components eigenvalues are smaller than the strong polynomial. We expect that it converges slower than strong polynomial.
But that's comparing the eigenvalues this way. But I think if you look at the shape of these, the polynomial eigenvalues look like this, and they cut off around here, whereas the other variant, they come out all the way to here. So there are more eigenvalues that are larger.
Okay, so you mean those part of eigenvalues are kind of dominant the difference in training, because
that's what I think. Yes.
Okay. But look at the data and
yeah, the other variants.
I don't know if data should be even better, right? You directly.
Well, I'm wondering if I was thinking if there was some type of way to normalize these eigenvalues so you can actually compare them in terms of the magnitude, because I'm wondering if, although these are, they're more large eigenvalues, maybe if you normalize them, the largest eigenvalue of these strong enforcements are maybe much larger than the other variants, which could account for the better training.
Oh, okay, yeah. Then maybe you can just divide each eigenvalue by the summation of all the eigenvalues. That is just the trace of the NTK matrix.
Yeah. Okay.
Then maybe we can see the difference more clear.
Right. Yeah, I'll try that and see. And yeah, that was all I have for today.
Okay, great. Any question? Yeah, I think this is interesting, but I think they kind of like using the theories and guarantees at the limit to showcase the behaviors of the pins. I feel a little bit. I mean, there is some gap there because I know that to solve a Poisson equation, you don't need like 500 neurons per layer. Like at most 50 is enough. Like even with 20, even with 20 and 4 layers, that'll give you very good performance.
Right.
I think there's still some kind of gap between the theory and the practice of pins.
Yeah, I think definitely. So I was hoping that the NTK analysis in conjunction with other analysis tools would kind of balance that sort of gap out.
Yeah, I'm curious why looks like NTK is talking about the kernel things, right? If we directly use kernel methods to solve that, we wouldn't need to worry about those discrepancies.
Sorry, say that again. Directly use kernel methods for.
Yeah, like for using Gaussian process to solve this Poisson equation or what else, other equations. Maybe, yeah, maybe some more powerful tools can be leveraged for analysis. But for NTK here, oh, another thing I want to ask. Yeah, when you look at strong pins, actually your loss. Can I take a look at your construction of strong pin? Previous slide. Yeah, this guy. Okay, so the loss is still the same, except that you have a different way to construct this U. Okay. So then you don't need to worry about the form of gradient flow. The gradient flow is the same as before.
Mm-hmm.
Okay. Yeah, we can definitely think about that. How can we characterize the behavior of the strong pins? Because intuitively, it should work better than the standard pins, right?
The strong pin, you're saying?
Yeah.
Yeah.
I mean, in terms of a relative RMSE, you haven't seen this, right? At least it converges faster.
Right. Yeah.
Okay.
The issue is it's not always possible to formulate this strong.
Yeah, I know that. But for many commonly used boundary conditions, you actually can construct strong pins this way.
Mm-hmm.
I think this is a good. At least this is a good. It's a good variant of pins.
Mm-hmm.
You don't need to worry too much about struggling the battle between the boundary loss and the residue term.
Right.
And then the next step, we need to use some tools to justify the advantage of strong pins.
Right.
Okay. Any questions from others?
So can you switch to the slide just before the eigen decomposition?
I think this is the slides, right?
Just before the eigen decomposition. So it's like the derivative equals to the this part. Yeah, it should be this part. So on the left side it's the derivative with respect to the time, and the right side is k multiplies with the deviation from the ground truth. So this paper is trying to balance the two optimization parts by manipulating the eigenvalues of the k.
Yes.
Because k is the limiting value is constant. So we are trying to, he is trying to if the at a specific time, the left part is a constant, and the right part the left part is some value, and the right part, the second term, is some value. And if we increase the eigenvalue for the second part, then we can do more optimization upon the second term, right? Like for the residue term. So they are trying to come up with a algorithm that can adjust the weight for the two parts automatically.
Yeah, so in this work, they they don't fix the issue of this eigenvalue, the steep slope of the eigenvalues.
Yeah, because if you change the weight for the two terms, then the k star just change, and the eigenvalue of k just change.
And you're saying they don't
Yeah,
change?
because the total loss should be the like the L2 loss for the function value and the L2 loss for the residue part.
Mm-hmm.
And they are trying to learn in the lambda weights for each term. And if we update the weight term, the k star here should be changed. And as a result, if we need to like update more about the second term, then the adjustment about the weight should the result should be to increase the eigenvalue of the second term.
Right, that's what they're attempting to do. But this reweighting method doesn't actually increase the eigenvalues. In practice, it does break this assumption that the NTK stays constant. I believe. Is that what you're saying, or I don't think I quite understand.
Yeah, I just want to confirm my my thoughts. Yeah.
Okay.
Yeah. The algorithm is just trying to adjust the weights and make the eigenvalue of any part that they want to optimize more to just increase the eigenvalues of those parts.
So they want to increase the eigenvalues of those parts, but this method doesn't actually address that. They show that since there's such a large discrepancy in the eigenvalues between the two terms, that the boundary term specifically should be weighted higher. So it's more of a focus during training. And to do that, they use this NTK to come up with the weights. But this method doesn't actually fix or change the eigenvalues themselves.
Okay.
Or the shape of the eigenvalues, I guess.
Okay, thank you.
Okay. Any other comments or questions?
Yeah, I kind of lost in between. So basically, they prove that the K0 is equal to K star, so K does not change during the training, right? And so how the spectral analysis become useful? So like why we need to compute the eigenvalues? So we can use the K star to K0 for training. Why we need to compute the eigenvalues of K?
The eigenvalues determine they give you the rate of convergence. The K alone doesn't tell you too much, I would say, at least what's like in the current research so far.
Well, you can take a look at this is ODE, right? This is
yeah, that's ODE, right?
Yeah, so they do analysis by solving this ODE, because it's if you assume K is a constant, K star, then this ODE is very simple. It's just a linear time invariant ODE.
Yeah.
So they can directly give the solution. So Madison, if you can, no, one slide before. Yeah, that one. You can see that they can directly derive something in terms of this linear invariant ODE. Then they do some kind of like arrangement, like you subtract the both sides by by like G and F, they can give this equation in the bottom.
Yeah.
And then you can see the left hand the left hand side of the bottom line is kind of like a training error.
Yeah.
So because they can apply the eigen decomposition over Q. This is U and UXX. Maybe Madison, you can go to one slide before, one more slide before. Yeah, one slide before. And one slide before. Oh yeah, next slide.
Okay.
No, next.
This one?
39. Yeah.
Okay.
Yeah. So they can show that based on this LTI ODE, they can derive this. I don't know how they derive, but it's based on some. I guess it's based on some ODE properties, and then they further simplify this ODE by subtracting both sides by this G and F. G is the boundary, and F is the collocation, the residue term, and you can see that now the left hand side, I mean in the middle, it becomes the training error actually, and the right hand side, if you take some eigen, you get rid of this identity, and then you take eigen decomposition over this matrix exponential, they have this form. So after some kind of simplification, they give the result in the bottom line. So that actually reflects the left hand side is actually some kind of transformation of the training error.
Yeah.
A Q is just the eigenvectors. You can view like some kind of like a full rank transformation. And the right hand side just indicates, because it's dominated by the exponential term, right? It just tells you how fast each component in the left hand side goes to 0.
Okay.
So all those results are just to show. I mean, this ODE or gradient flow just is an intermediate results for you to derive this this final line of equation, and which can reflect how your training error goes to converges to 0, how fast.
So they won't just give a theoretical justification of how those two, the residue term and the calculation term, affect the training error?
The residue term and
the residue term, okay.
The error
boundary
term, boundary term, they consist of they form the training error, right?
Yeah,
so just tells you, okay, how fast each error term goes to 0.
Okay, I see. Okay.
Yeah, and it's dominated by this lambda, big lambda. Big lambda is actually eigenvalues.
Okay, cool. Thanks.
Okay, yeah, I think it's a very good talk, Max. Now I know what I fully understand what you are doing right now, and yeah, we need to come a way to justify the advantage of the advantage of strong pins. Maybe not only in terms of maybe not only in terms of the NTK, but also in terms of other tools like Fourier analysis. Yeah, but anyway, I'll think about it, and we may discuss sometime next week.
Okay, yeah, that sounds good.
Okay, great. Thanks for your talk, Madison. And tomorrow we'll have Nancy to present to the deep symbolic regression. Nancy.
It should be Friday, right? Friday morning.
Friday. Oh, not tomorrow. Sorry, Friday. Friday 10 to 12, and she will introduce the symbolic regression with reinforcement learning and based on recurrent neural networks. Okay. Yeah, let's stop here today. Thanks.
Thank you.
Yeah. Bye.
Thank you.